Hello everybody, welcome to Math for Programming course. In this video, I'm going to discuss statistics for computer programming. So how can we apply statistics in computer programming? It plays a really crucial role in computer programming, particularly in data analysis, machine learning, algorithm optimization, and decision-making systems. It provides tools to help us summarize data, infer the patterns, model uncertainties, and make predictions. So in programming, we can use libraries like NumPy, SciPy, Pandas, and StatsModel in Python to make statistical computations more efficiently. Okay, so that means we don't always need to write our own programs to handle the data and perform statistical analysis. So let us talk about the first topic for this video, which is descriptive statistics. So descriptive statistics would involve the summarizing and organizing of the data to describe the features of the data, like the central tendency, which means the mean, median, and mode of the data. And we can also measure the dispersion of the data, characterized by the variance, standard deviation, and the range of the data. So let me use this example here to describe the meaning of the descriptive statistics. So first, we can find out the mean from the data, and the mean is also called the arithmetic average of the data. So the definition is rather straightforward. We add up all the values and we divide the sum by the number of observations. Okay, so the formula can be written as this one. We sum up all the values and n as divide the sum by n. N is the total number of data. Okay, so we have these numbers, and I would like to calculate the sum, which is equal to 74. And since I have 7 such numbers, the mean will be just 74 divided by 7, which is around 10.571. So we can say that the mean is just 10.57 if we round it to only 2 decimal places. Okay. And the second type of descriptive statistics is called the median, which is essentially the middle value of the data. So the middle value should be found when the data is ordered. And for an odd number of data, the median is just the middle value of the data. But for an even number of elements, we just take the average of the middle two values as the median of the data. So the formula is like that. If we have an odd number of elements, the median is just the element with index n plus 1 divided by 2. And if n is an even number, the median will be the average of the two middle numbers denoted by index n over 2 and n over 2 plus 1. Okay. So let us try to use the same data to demonstrate the meaning of median. Now we need to sort the numbers so that I'm able to have 10 as the middle value. Okay. Since I have 7 elements, the position is just 7 plus 1 divided by 2, which is coming from this definition, to get the 4th value to be picked up. Okay, that means the result of the median is just 10 from these 7 numbers. Okay, and then we can talk about the mode, which means the most frequent value in the data. So the definition is like that. The values that would appear most frequently in the data will be the mode. So let us see the example here. Since from my data, each value would just appear once, we would say that we have no mode. Okay, all the numbers are not repeated. That means we have no mode. Okay, and the range is like that. It is meaning the difference between the maximum value and the minimum value of the data. So in the formula format, it is just like x max minus x mean. Okay, so from the data here, the maximum value of x is just 18, while the minimum value is just 4. That's why the range is just 18 minus 4, which is equal to 14. Okay, and we have another quantity called variance. And let us see the definition of the variance. It is the average of the squared deviations from the mean. And the variance would measure the spread around the mean. So we have 2 types of variance. One is called the population variance, which is obtained by this formula. We pick up each element and I subtract the mean from each of the data, and then I take the square of the difference and I sum up all these differences for each piece of input data. And then I divided the sum by n here, okay? So mu here is the population mean, okay? So that is the meaning of the population variance. And similarly, I will have a sample variance called at squared. Here you will see that the denominator is not n, but n minus 1. So the way to find out the sample variance by using the variance definition in this way is actually applying the Bessel's correction. So if we just know the sample mean rather than the population mean, the sample variance will be evaluated by dividing the squared deviations from sample mean by n minus 1, okay? And let us see the step-by-step guide of the evaluation of the sample variance. So suppose we still have these 7 numbers here, and I can pick up the sample mean, which is equal to 10.57 from the previous discussion shown here, okay? And I pick up the differences, and then I square all the differences here, here, and here, okay? And then I add up all these squared deviations, and the sum will be just this quantity. And then I divide this sum by 7 minus 1, which is 6, to get the sample variance as 23.271, okay? So that is the answer. And how about the other concept called standard deviation? That is easy. It is just the square root of the variance. And the unit of the standard deviation is just the same as that in the original units of the data, okay? And the population standard deviation is just the square root of the population variance, okay? And the sample standard deviation is just the square root of the sample variance, okay? So we have already calculated the sample variance in the previous discussion shown here, okay? Then if we want to get the sample standard deviation, I just need to take the square root of the sample variance to get 4.824. So that is the sample standard deviation, okay? So how can we apply descriptive statistics? We have several situations. We can use it in the data preprocessing in machine learning pipelines to help us understand the dataset characteristics. For example, we can identify outliers or we can normalize features by using descriptive statistics, okay? And we can also use descriptive statistics in performance monitoring in software, like calculating the average response time in the web servers. And we can also summarize logs or use metrics in applications, such as the average session duration in the mobile app. So we can use descriptive statistics to quantify these things, okay? And we can use descriptive statistics as visualization tools, where the stats like the quartiles, the range, the standard deviations, and so on are used to generate box plots for dashboards, okay? So let us see how we can implement descriptive statistics in Python. So let us see this part. We can import NumPy and pandas into the coding environment, and then I can input some data in a list, and then I can just use the NumPy module to call the mean function, median function, and std function, which means the standard deviation. So I can just input the function name together with the list that stores the data, and then I'm able to run all these lines to get the mean, standard deviation, and the median, okay? And then I can use the series function coming from pandas to create a data frame for my data. And in the data frame, I'm able to use the descript function so that I'm able to show the descriptive summary of the data. So let me try to run the program. Yes, you can see the mean, standard deviation, and the median. And this part is about the descriptive summary coming from pandas, okay? So you can see that pandas is able to help us summarize the data by showing the number of pieces of data, the mean, standard deviation, minimum value, the lower quartile, the median, the upper quartile, and the maximum value of the data. Okay, so you can see that the descriptive summary is quite helpful to let us see the basic information from the data. Okay. Now let's talk about another section called inferential statistics. So what is it about? In inferential statistics, we use some sample data to make generalizations about a population, including the use of hypothesis testing, confidence intervals, and the p-values. So these key tools would help us quantify the reliability of our inferences. So the first thing to discuss is the hypothesis testing. So it is a formal procedure to evaluate a claim, which is also called a hypothesis, about a population parameter using the sample data. It would involve the setting up of two competing hypotheses. What are they? One is called the null hypothesis. We also call it H0, and it is the default assumption, and it is often trying to state that we have no effect or no differences in a given operation to take. So for example, we can say that a population would equal a specific value. Okay, that is our null hypothesis. We don't hope things to change after something is done. So if that's the case, we would say that we would have the null hypothesis. And the other one is called the alternative hypothesis. We call it H1 or HA here, okay? And what is it about? It is just the claim we are testing. And the alternative hypothesis would suggest an effect or difference. For example, the population mean is greater than or less than or not equal to a given value that you already stated in the null hypothesis, okay? So null hypothesis means that we don't have some effect to come up after some action is done. And the alternative hypothesis is going to claim that some effect is really achieved after some action is done, okay? So the process of hypothesis testing would involve the calculation of a test statistic from the sample data, and we also need to compare the test statistic to a critical value, and we can also use a p-value, which will be discussed later, to decide whether or not we need to reject H0. That is the null hypothesis, okay? And for hypothesis testing to be taken, we need a common test statistic for a population mean when the population standard deviation sigma is given, and that test statistic is called the z-score, and the z-score is evaluated by this formula. X bar here is the sample mean obtained from the data, and the population mean mu0 here is a hypothesized population mean under the null hypothesis. That means we use that hypothesized population mean to claim that there is no effect under a given action, okay? And sigma here is the population standard deviation, which is a quantity given before you take the test. And n here is the sample size, okay? So you use all these four variables to calculate the z-score, okay? So what would happen if the standard deviation of the population isn't yet known? If that's the case, we can use the t-statistic instead of the z-score to be the test statistic. So t-statistic is something like this one. The sample mean minus the hypothesized population mean under the null hypothesis divided by the sample standard deviation, which can be taken from the sample, and we divide it by root n. N is the number of samples, okay? So we use this test statistic instead of the stat score if we don't know this population mean in advance, okay? So let us take a look at this example. Suppose we want to test if the average height of the adult man in a population is 175 cm or not. So we suppose that the change doesn't exist. That's why we would say that the null hypothesis is mu equals 175 cm, okay? And the alternative hypothesis is that the average height of adult man greater than 175 cm. So if we want to claim so, we set it as the alternative hypothesis. That's why I would say mu larger than 175 cm as the alternative hypothesis, okay? And then we take a sample of 100 men randomly, and I can get the average height as 177 cm coming from the sample. And if I also know that the sample standard deviation is 10 cm, I can just use all these pieces of information to get the z-score. And when you use the formula shown here, you put n equals 100, sigma as 10, x bar as 177, and mu0 as the hypothesized population mean as 175 cm. I'm able to show 2 as the z-score. So if I get a set score, I need to use it in the one-tailed test at the 5% significance level. So that means our alpha value for the significance level is 0.05. And we can use the critical Z value for 0.05 or 5%, which is equal to 1.625, to compare with the standard score that we obtained from the data. So since 2 is larger than 1.645, it means that the set score is treated as a significant result at this level of significance, okay? And in this case, we would reject H0. That means we reject the null hypothesis, and we would conclude that there is some evidence from the data that the population mean height is really greater than 175 cm, okay? So that is the process of using the set score to do the hypothesis testing. And another topic to discuss is the confidence intervals. So a confidence interval is also called CI. It can provide a range of values within which the true population parameter is likely to lie, okay, based on the sample data. And it is associated with a confidence interval, say 95%, which indicate the proportion of such intervals that would contain the true parameter if we repeated the sampling process many times, okay. So that is the meaning of the confidence interval. That means if we create so many sampling actions, and we make confidence intervals for each of the sampling results, 95% of the confidence intervals will contain the true parameter, okay? That is the meaning of the confidence interval. So for a population mean with a given population standard deviation, the 95% confidence interval is that one. X bar coming from the data, and plus or minus Z alpha over 2. Alpha over 2 is just this alpha divided by 2, and we look for the critical Z value by using alpha over 2 here, okay? And this sigma is just the population standard deviation given already, and n is the number of samples that you take from a population. So ZA over 2 is the critical Z value for the desired interval. So it can be 1.96 for 95% of confidence interval. So this 1.96 comes from the fact that we take both sides of the normal distribution. So when alpha is equal to 0.05, alpha over 2 is just 0.025. And when we want to find out the critical Z value for 0.025, I would get 1.96 as the answer. Okay, so that is the meaning of the critical Z value for this confidence interval, okay? And if sigma is not known from the data beforehand, we can use the t-distribution instead. So the confidence interval for using the t-distribution is something like that. It is similar to the previous one by using the population standard deviation, but now this test statistic is like that: t alpha over 2 and df. df means the degrees of freedom, which is equal to n minus 1. N is the number of pieces of data that you obtain from one sampling, okay? And S is the sample standard deviation, and N is the number of samples that you take. So you use this one instead to represent the confidence interval if you don't know the population mean in advance, okay? And this critical value is to be found by using a student t-distribution, okay? And let us see this example. Suppose I have the same problem, but now I want to get the confidence interval at 95% confidence. So in this case, I just put X bar Z alpha over 2, which is corresponding to the confidence interval of 95% confidence, taking at both sides of the normal distribution. So it means that the alpha over 2 is 0.025, okay? So when you look up 0.025 for the level of significance, you will get 1.96, okay? So you also need to put S, sigma, and N to get this range, okay? So the confidence interval will be just that one, coming from this plus or minus sign. So this confidence interval is meaning that our current sampling would suggest this interval for the population mean. If we redo the sampling for many times, 95% of the total number of the subsequent intervals would be able to contain the true population mean. So that is the meaning of the 95% confidence interval. And we have to notice that this interval does not include 175 cm. So this interval would align with the fact that the null hypothesis is already rejected. So remember that we already rejected the null hypothesis shown here, okay? That's why we would try to think that the alternative hypothesis cannot be rejected. So that is the reason why the confidence interval here is not containing the null hypothesis value, okay? And the next topic to discuss is the p-values. The p-value is really the probability of obtaining sample data as extreme as what was observed, okay, assuming that the null hypothesis is true. You can measure the strength of evidence against the null hypothesis, and a small p-value, typically less than alpha like 0.05, would be able to suggest that the data is unlikely under the null hypothesis, leading us to reject the null hypothesis, okay? So if a critical value enters the critical region, characterized by the probability of, say, 0.05, it is likely that the null hypothesis should be rejected. And the p-value is calculated based on the test statistic and the distribution of the test statistic. So for a z-test, it is the area under the standard normal curve beyond the observed z-value, okay? So this is an example of a normal distribution curve, and if we have a z-value that is entering the critical region, we will be able to reject our null hypothesis, okay? So for a one-tailed test like this one, the true population mean is larger than our asserted value, then the p-value is equal to that one. The probability that the standard normal random variable called z is larger than the observed value of the z-score from the data, okay? And if the z-score observed from the data is larger than our alpha, like 0.05, then we just reject H0, and we would try to believe that the alternative hypothesis is a better claim, okay? So let us see this example. We can continue with the height example that we showed previously, and we already know that the z-score is 2, and the corresponding p-value for the one-tailed test is the probability that the standard normal random variable is larger than 2. So by using the standard normal table, or by using a calculator, or by using a computer program, we would see that the probability that the standard normal random variable that is larger than 2 is equal to this probability, which is about 2.28%. And since 2.28% is less than 5%, we would be able to reject H0. And this rejection is consistent with our earlier test. In the earlier test, we also rejected the null hypothesis, okay? And if the p-value were 0.1, for example, like the smaller z-score like 1.28, we would fail to reject H0 as it is not sufficiently small, okay? So if the p-value here is not 0.028, instead if it were 0.1, then we would not be able to reject H0 as the z-score isn't able to enter the critical region shown here, okay? So if the p-value here from the data is 0.1, then the corresponding z-score may be somewhere here, so it is not able to enter the critical region yet. That's why we will not be able to reject the null hypothesis in this case, okay? So how can we apply inferential statistics in programming? We can do A/B testing in web development to compare the user engagement between two versions of a page. So we can do some statistical tests to see whether the version A is better than the version B or not. And we can also use inferential statistics in quality assurance in software testing, inferring defect rates from the sample runs, okay? And we can also use inferential statistics to do predictive modeling in data science. We can use it to estimate the parameters for large data sets. And we can also use inferential statistics to do anomaly detection in cybersecurity by using the z-scores to flag some unusual network traffic. So let us see how we can implement inferential statistics in Python. So let us see this example. Now I have some sample data. I have 5 pieces of data, okay? And I can get the confidence interval of the mean of this group. So the idea is to use the library. We can use the stat module, and in the stats module, I can use the team module, which is a submodule actually, And in this submodule, I have a function called interval, okay? And I need to put the confidence, which is 95% or 0.95. And then here I would like to put the degrees of freedom, which is the number of things minus 1, okay? And then I need to put the location of the confidence interval about the sample mean, okay? And the scale here will be adjusted by the standard error of the mean shown here, okay? So we have a feature from the stats module to help us get the standard error of the mean, okay? The standard error of the mean is actually the sigma divided by root n, which is this one. Okay, this one is actually the standard error of the sample mean, okay, s divided by root n, okay. And when we have all these pieces of information, I'm able to show the confidence interval by using the interval function. So let me run it. Yes, you can see the interval is given here. So the lower bound is that one and the upper bound is that one. So this is the confidence interval coming from this set of data, okay. Now let's talk about number 3, which is called regression analysis. So the regression models would help us get the relationship between the variables, such as linear regression for continuous outcomes or logistic regression for binary variables, okay. So let's talk about the linear regression first. A linear regression would try to assume a linear relationship between the independent variables and the continuous dependent variable. And it can estimate the best fitting line that minimizes the sum of the squared differences between the observed value and the predicted values coming from data. So if we want to delve into this topic, we have to learn the ordinary least squares method, or what we call the OLS method, okay? But in this video, we won't go into such a detail. I just want to show the result. So for simple linear regression, by having one predictor means the x here, which is a variable that will be input into the model. So that is the independent variable. So we have only one independent variable here. And y is the output, okay? And I want to use a straight line to model the relationship between x and y. So I have the y-intercept called beta 0 shown here. And I've also got the slope, which is called beta 1, okay? It means the change in the y value for 1 unit increase in x, okay? And this epsilon is the random error term, okay? We assume that the error is normally distributed with the mean 0, okay? So that is the model for simple linear regression that has only one predictor. How about the situation when we have multiple predictors? We can use the multiple linear regression model. So you can see the model is like that. I have the y-intercept, and then I have different slopes for different predictors, okay? So when I have one predictor, I have to include one slope for that particular predictor. And then I add up all these effects coming from the predictor and from the slope, okay? And I also need to include the epsilon, which means the random error term of the model, okay? So the model's goodness of fit is often assessed by using the R-squared value, which can represent the proportion of the variance in y that can be explained by the predictors. So this R-squared would range from 0 to 1, where 1 indicates the perfect fit. Of course, in the real world, it is not easy to get the fitting that returns the R-squared as 1 exactly. Usually the R-squared would be less than 1 in our real life, okay? So let us consider this example. Suppose I have a synthetic data set examining the relationship between the number of hours studied and the exam score. So we can assume that both variables are continuous. That means the independent variable is a continuous variable, and the dependent variable here is also a continuous variable. And we have these data points. So it means that when I study for 1 hour, I will get 2 points in the exam. When I study 2 hours, I will have the exam score as 4, so on and so forth, okay? So when we do the fitting, we will be able to see that the beta 0 would be 0.3, which means the y-intercept would be 0.3, and the slope called beta 1 is equal to 1.7. So we can write the linear regression result as that one. Y equals 0.3 plus 1.7x plus epsilon, okay? So let us see the interpretation of this linear regression model. For every additional hour studied, the exam score would increase by 1.7 points on average, okay? And the R squared obtained from this linear regression model is 0.99. That means about 99% of the variability in scores can be explained by the number of hours studied, okay? In general, it means that when you study more, you will get a higher score in general. So to illustrate the prediction, I can use this example. So if I study for 6 hours, which is a value not included in the data points, I would like to predict the exam scores to be like that one. 0.3 plus 1.7 times 6, which is equal to 10.5. So if I study for 6 hours, I will be able to get 10.5 marks. And this result will come from the linear regression model that we made shortly, okay? The next topic to discuss is the logistic regression. It is used when the dependent variable is a binary variable. That means the dependent variable has two possible answers, 0 or 1, of failure or success, okay? So we have only two possibilities to become the value of the dependent variable, okay? So the logistic regression would model the probability of the outcome being 1 as a function of the predictors, using a logistic function, which is a sigma function in many cases, to ensure the probabilities would stay between 0 and 1, okay? And unlike linear regression, it doesn't assume linearity in the raw outcomes but in the log odds, and we will show the meaning of the log odds later on. So the model for the simple logistic regression is something like that one. P here means the probability. The probability that the result is equal to 1 can be modeled by this logistic regression model. So here you see E as the base of the natural logarithm, and Py equals 1 is the probability of the event to occur. So that means we input the probability of having 1 as the answer to the left hand side, and I'm going to use this model and the values of x obtained from the data to evaluate the beta 0 here and the beta 1 here, okay? So we can use the maximum likelihood method to evaluate the beta 0 and beta 1 here, okay? So that means if we have many pairs of x, y coordinates, we can use them to evaluate the beta 0 here and the beta 1 here, okay? So that is the meaning of the log odds here. So you see that this logistic regression model isn't a linear model yet. How can we turn it to a linear model? We can do something like this one. Since we already know the logistic regression model, I can take a logarithm and then I can put this probability into this function, and you will be able to see that I will have beta 0 plus beta 1x. So you will see a beautiful linear regression model to come up. So after manipulating the ordinary logistic regression model, I'm able to see the log odds that would follow the linear regression pattern, okay? So for multiple predictors, we can extend the right-hand side to include more and more predictors and more slopes, okay? So let us see this particular example. Let us consider a synthetic dataset relating the dosage level x to the treatment success. 0 means failure and 1 means success. So the data points are like that. If I have 1 level of dosage, I will not be able to be successful. If I have 2 levels of dosage, the treatment is not successful. If I have a dosage level of 4, the treatment will become successful. If I have 5 levels of dosage, the treatment will also become successful. Okay, so that is the meaning of x and y here. So can we use a logistic regression model to fit the data? Yes, it is possible. So we can use the computer programs to find out beta 0 as this number and beta 1 as that number. So that should be beta 1, okay, not beta 0, 1, okay. So if I put beta 0 and beta 1 into this expression, I'm able to see the logistic regression model as that one. So the probability of getting a successful treatment would depend on the input of x in this following function, okay? So the positive beta 1 here, which is 46.6, would indicate that a higher dosage would increase the odds of success, okay? So more dose would mean a better chance of successful treatment, okay? So to illustrate the prediction, we can try x equals 3.5, which is the midpoint between 3 and 4, okay? So if I take x as 3.5, is it possible to be healed? Let us see. The log odds will be like this value. The log odds, which means the left-hand side here, will be equal to 0.3, okay? So when I have log odds, I'm able to get back the probability of success. So Py equals 1 is equal to that one, okay? So I just put this log odds into the logistic regression function to see that the probability of getting y equals 1 is equal to 0.57. It means that we have 57% of chance to heal the patient if I have 3.5 levels of dosage, okay? So how can we apply regression models in computer programming? We can use them in predictive analytics, like forecasting sales in the e-commerce apps by using the historical data. We can also use regression in machine learning, where the linear regressions can serve as a baseline for more complex models. So we can use them in the scikit-learn pipelines, okay? And we can also use the regression models in resource allocation in systems programming. We can also use it to model the CPU usage based on the workload, okay? And we can use regression models in recommendation systems to predict the user ratings from the features obtained from the users, okay? So let us see how we can implement regression analysis in Python. So this is the part of regression analysis. I need to import NumPy, and I also need to import the linear regression module from the scikit-learn module. And in this scikit-learn module, we have a linear model submodule. Okay, so this linear regression function is obtained from this linear model submodule, okay? And I also want to use the matplotlib module to help us plot the graphs, okay? So we have the sample data here. So this is the feature, and the feature is going to correspond to a target. So the sample data here would want to say if I have 1 hour of study, the final exam score will be 50 marks. If I study for 2 hours, the exam score would be 60 marks, so on and so forth. So I can use the linear regression model to see whether x and y values are really correlated. So I can use model.fit, okay? So the model is just representing the linear regression model that we already imported beforehand. And we use the fit function to fit x and y to get the model, okay? And we can use the model to predict the new values. So if I study for 6 hours, what would be the score? I can use this predict function to help us get the predicted value from the model, okay? And I can do the plotting, okay? So let me run the program. So you can see that the predicted score is 100 marks if I study for 6 hours. And you can see that from the data, we have 1 hour, 2 hours, 3 hours, 4 hours, and 5 hours. And for these hours of study, I would also be able to show the corresponding marks. So all these things are from the model. And the red line is the fitted line from the model, okay? So this model is able to show a good linear relationship between the number of hours of study and the exam marks, okay? So let us talk about another section called Bayesian statistics. So what is the meaning of Bayesian statistics? Let us see. It incorporates the prior knowledge with new evidence using the Bayes theorem. So it is used for updating the probabilities usually. And the Bayes theorem would formally combine the prior knowledge, that means the knowledge before seeing the data, with new evidence, which means the likelihood of the data given a hypothesis, okay? So we can use these pieces of information to produce a posterior belief, which is also called the updated probability after seeing the data, okay? That means if we have some prior knowledge, and if we also have some new evidence, we can combine these things together to update our probability, okay? And the updated result is called the posterior probability, okay? And let us see this formula. The core formula of the Bayes theorem is like that. We want to evaluate the posterior probability. What is the meaning of it? It is the probability of the hypothesis H given data D, okay? So if we have the data already, we want to estimate the probability of having this hypothesis to be correct, okay? And P of D given H is the likelihood, which means the probability of observing data D if the hypothesis H is true, okay? So that is the meaning of the likelihood here. If we know the hypothesis is true, what is the probability of observing the data D? That is the meaning of the likelihood, okay? And the prior probability is here, P of H, which means the initial belief in H before seeing D, okay? So when we don't know D yet, what is our belief of the probability of making the hypothesis to happen? That is called our P of H here. And the P of D here is called the marginal likelihood, also called the evidence. It is able to tell us the total probability of D across all the hypotheses concerned, okay? So we will be able to see the meaning of the marginal likelihood or the total probability or the evidence. So this is the formula about the marginal likelihood. When these are mutually exclusive and exhaustive hypotheses, H1, H2, and so on, P of D is computed according to this formula. I need to sum up all the likelihood times the prior probability of each possible hypothesis. And then I add up all these products to become my marginal probability, okay? So let us see this following example to see how we can apply this formula, because this idea is rather complex in my opinion. So suppose we are doing some medical diagnosis. A pretty rare disease would affect 1 person in 1,000 people. That means the probability of having a disease is 0.001. So the probability that a person has no such disease is equal to 0.999, okay? And then we developed a diagnostic test. The test is like this. It is 99% accurate when the person has the disease. So it means that the probability that the result is positive given that the person has the disease is equal to 0.99. And it is 95% accurate when the person does not have the disease, okay? So that means that the probability that we will get a negative result if the person has no disease would be equal to 0.95. So the false positive rate is equal to 1 minus 0.95, which is equal to 0.05, okay? So we have these two conditional probabilities now. We can really calculate the probability of having a positive result given that the patient has no disease. In this case, we call it the false positive result, which is equal to 1 minus 0.95, which is just equal to 0.05. Now the question is like this. A patient has a positive result. So what will be the probability that this person really has the disease? Let us see how we can do it. So let H1 equals disease and H0 to mean no disease, okay? And the probability of having a disease is 0.001, and the probability of having no disease is equal to 0.999. And D means a positive test. We want to find out the probability that a person really has a disease given that the test result is really positive, okay? So we can use the Bayes theorem like that one. P of H1 given positive is equal to P of positive given H1 times P of H1 divided by P of positive, okay? So we want to compute the denominator first, which is relying on this formula, okay? P positive is equal to P of positive given H1. That means the probability of positive result given that the person has a disease. And it is multiplied by P of H1. And I want to add another term, which is equal to P of positive given H0 times P of H0. So P of positive given H0 means that it is the probability of getting a positive result given that we know the person has no disease, okay? So when I plug in all these numbers into the equation, I'm able to see that I will have 0.05094 as the probability of getting a positive result, okay? So this positive result has considered the situations that the person has the disease or the person does not have that disease, okay? So 0.001 is H1 and 0.999 is H0 and 0.99 is coming from the accuracy here And 0.05 here comes from the result of the false positive rate, okay? False positive means that the positive result is false. That means if the person has no disease, the test will still give us a positive result. That is the meaning of the false positive result, okay? So when we plug in all the numbers, we will be able to get the probability of having a disease given the positive result is 0.0194. Okay, so that is the meaning of using the Bayes theorem. So let us see how we can interpret the result. So even with a positive test, there is only about 1.94% of chance that the patient has the disease. So it means that the most positive results are false alarms due to the low base rate. Okay, so it means that the positive result coming from the test isn't so reliable. Okay, because out of all the positive tests, we have only 1.94% of those positive tests that would refer to a person that really has got the disease. Okay, so how can we apply Bayesian statistics in computer programming? We can use it in the spam filtering and email clients by updating the probabilities based on the user feedback. Okay, so the user feedback would help us update the prior probability to become our posterior probability. We can also use Bayes' theorem in recommendation engines like in Netflix by using the priors for the personalized suggestions. Okay, so the priors here mean that we already understand from the big data that some people like some particular categories already. Okay, and we can also use Bayes' theorem in uncertainty quantification in AI, such as in probabilistic programming libraries like the PYMC library. That is a Monte Carlo simulation library for Python. Okay, and we can also use Bayes' theorem in sensor data fusion in robotics by combining the prior maps with the new observations to get the posterior probability. So let us see how we can implement the Bayes' theorem of Bayesian statistics in Python. Since my current program doesn't need to use the Monte Carlo simulation, I can just ignore this first line. Okay, so let us see how we can do the Bayes' theorem by using the prior probability, the likelihood, the false positive result, and the evidence, which is just the denominator of the Bayes' theorem. Okay, so we can refer the program to the notes here. Okay, so we can see that the posterior probability is the answer coming from the Bayes' theorem. The likelihood here is just this probability. Okay, and the prior probability is just that one, and the evidence is just coming from this summation formula. Okay, so the summation formula is like this one: the likelihood times the prior probability plus the false positive result times the 1 minus the prior probability. Okay, so the idea is similar to that one. Okay, then I'm able to show the answer of this Bayes' theorem result. Okay, so let me run it. So you can see that the posterior probability coming from the Bayes' theorem is 0.1538. Okay, so the idea is to just find out the likelihood, the prior probability, and the false positive result, and then I want to get the evidence as the denominator of the formula, and then I'm able to use the division to get the posterior probability. Okay, so this posterior probability is telling us that if we know the test gives us a positive result, what is the probability of that test that really refers to a sick person. Okay, so this video has discussed a lot of things about statistics. We have learned descriptive statistics by finding out the mean, variance, median, and so on. We also know how to get the variance, which can be classified into population variance and sample variance. We also learned inferential statistics, which can be divided into hypothesis testing that involves null hypothesis and alternative hypothesis. We also have the confidence interval, which can refer to the interval from a given sampling result. And we also know the meaning of the p-values, which is the probability coming from a normal distribution curve given the level of significance. Okay, so this level of significance is represented by probability. So if it is 5% of level of significance, then this area will be 0.05, okay? And when we have 0.05 as the area, we can find out the corresponding critical value that can help us get 0.05 as the probability, okay? And then we can use the critical region to help us determine whether we need to reject H0 or whether we don't reject H0, okay? And we also learned regression analysis that involves linear regression and logistic regression, okay? So we can use the data to try to fit them to a straight line, or we can fit the data to this model so that we will have a binary output based on the given data, okay? And we've also learned Bayesian statistics, which involves the use of the Bayes theorem here, okay? And the Bayes theorem would help us update the probability given that we know the prior probabilities and the likelihood of that probability to get a particular result. This is the end of the video. If you have any questions about my video, please leave your questions on the comment section below the video. If you like this video, please give me a like and please subscribe to my channel. Thank you for watching.